Hello, everybody, and good afternoon. My name is Nian-zhong Chen, and I'm from the TB University, and from the Department of Naval Architecture and Ocean Engineering. Today, I would like to share some work of our group, on the cohesive zone model and for the predicting hydrogen assisted photographic initiation in the subsea pipeline with initial defects. I would like to give you some, background. Uh, Corrosion fatigue actually is very severe, problem in the deep sea, pipeline actually, for because we have the very harsh environment and high pressure and high temperature. And also, and for the corrosion fatigue, and we have the three, scientific gap actually. First one is a lack of the qualification for the micro and the defects. Second is the heavy reliance on the empirical model. And also, we lack of the unified multi-physics, framework. So you can take a look here, 2021 and even 2024, 1 year ago, and we have, and a big accident, in the ocean area. You can see this is always due to, the corrosion fatigue problem. Also, we know that, now we call power to the gas P2G projects because this is very good, the solution for the developers offshore, renewable energy. For example, they can addressing wind, curtailment, and also it's a very good clean energy solution. So, like hydrogen, transportation by a long distance, pipeline is a very useful solution for the sustainable offshore hydrogen production. So these two background, so that's why I think it's very important to study the hydrogen problem. Okay, I'll give some label to hydrogen, right? Normally, hydrogen now is like currently the mechanism, and we all recognize it's HED and HELP, but maybe more mechanism will be and work together, combined together. But normally HED is identified as a primary driver for the governing the brittle failure process. And we can see it from here, so the combined factors will be loading and hydrogen, incremental, and also the microstructure like defects and everything will be induced, very quickly or like rapidly, failure of the pipeline. Actually, this is actually when I was working in the industry a long time ago, actually, in the 2013, I think 2013, the company, we very famous company, oil and gas is called BP, British Petroleum. They have a lot of the deep sea pipeline. The design life is 30 years, 30 years. But due to the corrosion fatigue problem, many pipeline only have 4 or 5 years leaking. So that's terrible. Yeah, that's terrible. That time I working for the ABS, we call American Bureau of Shipping, and in Houston, and they sent us an accident to our company at that time, and then we don't know how to do it actually. So how to see in 2013, and ExxonMobil and GE Oil and Gas, my company and the WOM, we established a commitment, and for the 20 KSI qualification, the committee, I was a member, one of the members at the time, actually. So this is actually is very, important problem for our industry. Yeah, industry. And also we all know, the initiation, the life is much very important. Maybe, more than 70% of the fatigue life, there's much more important than the prolongation, actually. Prolongation. Okay, And in this presentation, I would like to introduce we use secondly the cohesive zone model to predict the hydrogen problem. I just quickly just get through some work. And in 2017, my PhD student Chen and me, we proposed the two-stage formal equation to predicting the hydrogen system, particularly growth site. And in 2017 and 2018, and we proposed another model, including the analytic, this dissolution. And this is our some papers at the time. In the 2013, 2023, and we developed the cohesive zone model to predict the hydrogen system, the geographic growth. And this is our model. Just this year, we also proposed the fourth stage, elastic plastic constitutive model accounting for the hydrogen-induced dislocation, pinning, and depinning effects. Yeah, just published in paper. This presentation, I would like to introduce some defects. And the defects actually here. For example, and sorry, I just want to hear maybe better. This work today is a presentation. I just would like to introduce some defects because, for example, the material is not normal. So micro defects will be described as a semicircular area. And whereas the density of the chapter MT will be set up different from the normal area. Normal area. So for example, like the density of the chapter MT, we would like to defects where we would like to KNT multiplied by NT0. Okay, this is our idea, just like replace something. And also, we also would like to introduce the defects. For example, here have defects. We have another defects maybe nearby, and we see how this defect will be influenced on this. Okay, on this. Okay. Okay, come back. So we just diffusion equation. We just using this is very typical. The equation. And also, we're using the constitute this model we proposed in the 2023 and 2024. We developed some model on this. Just this year, and also we applied the fourth stage, elastic plastic constitutive model, and in this work. Okay, this constitutive equation is composed of four stage. The first stage will be pinning, hardening. Second one will be Plato. Plato is this one, and then depinning, and then depinning hardening. We using this model here. Okay, then we first we compare the experimental data, and this experimental and performed by the Zheng in the 2023. This is the experimental, the model, and the loading condition, and also material properties of the material. And this is our, the finite element model, and here we put the cohesive element here. Eventually, we take a look here at the results. So the relative error and between the model prediction and with the experimental data. So if you take a look at this table, the maximum, the relative error only 60 percentage. So it looks like it's still good. So its model prediction is, in general, is good agreement with the experimental data. Then we investigated some, investigated some, like for example, like density of chunk. What's the impact on the fatigue line? So we can take a look here. We can take a look here. With the density of hydrogen chapter increase, and the fatigue life is significantly reduced. Significantly reduced. You can see very, very quickly. The maximum reduction in the fatigue life may be over 10 times of is induced by the increase of the NT. We think the initial defect rate. So that means the density of chap is very important. Second, parameters that we would like to investigate is the size of the defects. For example, if the defects are a lot more large, so you can take a look here. More large, and the fatigue life will be reducing very, very significantly. Yeah, these no defects, and these defects will be 25 mil-m. And also, we also find here if the defects is very small, for example, like 5 mil-m, and also the impact is negligible. Okay, negligible. Okay, and then we take a look, how the second defects will influence the initial the defects. So, for example, most closely, that means more close, more influence. Here, this one only 50 mil-m, but this one will be 300 mil-m. So that means very close, actually, very close. More or less like the simple defects, effects. Yes. Okay. Yeah, so we just come to the conclusion here. The hydrogen system initiation of pipeline steel predicted by the proposed model agrees well with the experimental data. And also initial defects have a significant impact on the initiation of the hydrogen system fatigue cracks in pipeline steel. Fatigue crack initiation of pipeline will be markedly accelerated by the increase of the hydrogen chapter density in the initial defects region. And the second one is the degradation of the fatigue life will be critically depending on the defect size. So the effects can negligible for the defect below to a critical size. Effects of defect interaction lead to the decrease of the hydrogen assist fatigue life, but they become insignificant at a sufficiently large distance between the two defects. Thank you very much. And any questions?